So here we're going to do a quick introduction to solving nonlinear equations using Excel. We'll start with a single nonlinear equation and show a couple different ways that we can solve this. Here we have an equation x cubed minus 10 times the quantity x minus 1 squared equals negative 1. We can tell that this is a nonlinear equation because the unknown x is to a power other than 1. The first thing we want to do for solving these equations is to rearrange them to the form f of x equals 0. This isn't strictly required and not strictly required in Excel, but most other solvers besides Excel, some of which we'll see later on, do want the function to be in the form f of x equals 0. So we'll get in the habit of doing that here. We can always do that because we just take whatever's on one side of the equation and move it to the other side of the equation. So in this case, we move the minus 1 over, and then we have this function of x equals 0. When we only have a single equation, it makes sense to plot the equation. So we pick some reasonable range of x, which we have to guess, and then we evaluate f of x. So let's go from 0 to 0.4, and then we'll continue that down to 7.6, say. We'll see later if it's okay or not. And then evaluate the function. Equals x cubed minus 10 times parentheses x minus 1 squared plus 1. Enter. And we can fill that down. And then we can highlight the data and plot it, going insert, scatter plot, like so. So here we have a plot of the data, and our goal is to find the solutions to x are the values where x satisfies the equation, and here that is where the equation f of x equals 0. So we can see that f of x is 0 there, and there, and there. Now, because this is a cubic equation, we already know that we're going to have 3 roots, and so we can see the 3 roots on the screen. We know that there aren't any outside of the bounds. One approach to solving this equation is simply to zoom in on the graph, changing the axis limits until we get close enough to the root that we're happy with the results. And that approach works just fine. Another thing that we can do is just modify the x values until the function values are close enough to 0. So we can see that the root, one of the roots is right here because it changes from positive to negative in between 1.6 and 2. So we can try maybe 1.8, 1.9, oh that was too much, 1.85, and 1.8, 1.86, and we're starting to get close, 0.03. So that's an approach that can be done by hand, but that can be tedious. A better approach is to let Excel do the work for us. So now that we kind of know where one of the roots is, right around here, and there's another one over here, you can see where it changes sign, and another one here where it changes sign. We can come over and click on the data, and then we can go up to the Data tab, and then click the What If Analysis, Goal Seek. Here our goal is to make the function be 0, so we set cell C17 to a value of 0 by changing cell x that corresponds to it. So that would be B17. And then we hit OK. And Excel found a solution. We hit OK, and we can see that to within 3 or 4 digits, we have the answer here. X is 0.644. Will get us close to the solution. And you can see that Excel found, when we gave it the goal seek, Excel found this solution because the initial place that we started from was near this value of x. So if we want to find the other root, this root, then we can go up to this other value. Where does it change? Right here 1.6 and do the same thing. So what if analysis, goal seek, set that cell to target value of 0 by changing the corresponding x value. Okay. And we can see that it found the second root, 1.86566. And then we can do the same thing here. Goal seek, set cell to value 0 by changing its corresponding x value. Okay. And 7.490305. And that'll work great. Of course, you don't have to plot the results for that to work. You could pick any value of x. If you just put x, pick a value 1, and f of x, pick a value, just enter the equation, x cubed minus 10 times x minus 1 squared plus 1. Whoops, sorry, not x. We didn't name the cell. It should really be E18. E18. Okay. Then we can go to the goal seek, even if we didn't know what the plot looked like. What if analysis, goal seek, set cell to value 0 by changing cell x, and it finds a solution. In this case, it found this root. Plotting is a nice way to see how many roots there are if it's not necessarily a polynomial, and also to give you a good initial guess of where to start, because these nonlinear solvers won't always converge unless you give them really good guesses. So this is an approach for a single equation. Let's see what we do when we have more than one equation. Suppose we have these two equations in unknowns y and x. So our first equation is y equals x squared plus 3x plus 2. Our second equation is y equals 2x plus 3. And we want to find the values of both x and y that satisfy these two equations. Again, we have two equations with two unknowns. As before, we will rewrite this equation as f of x equals 0, where f now is a vector and x is a vector. So we're going to let the old x be called x1 and the old y be called x2, and x1 and x2 will be our unknowns. So a vector x with components x1 and x2, and a vector f with components f1 and f2. These are two different functions, where each function is a function of both unknowns, x1 and x2. So here we can see how this is represented. And then in the bottom, we do the same thing as before. We're going to pull the y's to the right-hand side by subtracting them. And then we just change the x's to x1s and the y's to x2s. So this is now our system of two equations and two unknowns. We have x1 squared plus 3x1 plus 2 minus x2 equals 0, and 2x1 plus 3 minus x2 equals 0. And when we write it like this, this will facilitate solving in other kinds of programming languages. So because we have only two equations and two unknowns, we can still kind of plot the data. So if we say we want f, so in this case, our solution is going to be where this equation equals 0 and this equation equals 0. So if we assume that the equation is 0, then if we pick a value for x1, we can solve for the value of x2, and for both of these equations. So we're going to do that here, and then we can plot what the curves look like when f1 is 0 and when f2 is 0, and the solution will be where the two curves intersect. So let's give ourselves a reasonable range for x. -3, -2.5, and we'll pull that down, and then we'll enter f1, so that's going to be equal to x1, well in this case x2 is y, so we can just do equals x1 squared plus 3 times x1 plus 2, and then we can do the same thing for the other set, -3, -2.5, pull that data down, and then do this one x2 again is y for the second equation, so that will be equals 2 times x1 plus 3. And we can pull that down. Now we can plot these functions, highlight the data, go insert, charts, and we'll do scatter with a line, and then we'll do another plot, insert, charts, scatter with a line, and then we'll click on this chart, copy, Control-C, Control-V, and it puts them on the same plot, which is convenient. Now when the two curves intersect, that's where x and y, or sorry, x1 and x2 have the same value for both functions. So f is 0 in both of those cases. And that's what we want. So this will give us an estimate of where the solutions are. And if we wanted to, we could zoom in on these. But in general, we want to do this for cases where we might have more than 2 equations and 2 unknowns, and it becomes too hard to graphically solve for the solution. We can't use goal-seek for this problem because goal-seek only works with 1 equation and 1 unknown, and here we have 2 equations and 2 unknowns. So instead of using goal-seek, we're going to use the solver. To use the solver, we have to add the plugin. To do that, we go up to File, Options at the bottom, and then we go to Add-ins on this left panel, and then at the bottom, we just hit the Go button. Go. We want the solver add-in. So check the box so that solver add-in is there, then click OK, and now we should have the solver add-in. There's 2 different methods that we can use the solver, and I'll show you both of them. The first method is we need to guess values for x1 and x2. So I'm just going to guess by looking at the plot. I'm going to guess that x1 is about 0.7 and x2 is about 4. Okay. Then we evaluate the function. So we evaluate f1. f1 is equal to x1 squared plus 3 times x1 plus 2 minus x2. Then we do the same thing for f2. f2 is equal to 2 times x1 plus 3 minus x2. Good. Now we can see my guesses weren't perfect because the functions aren't 0. They're supposed to be 0, but we'll let the solver take care of that for us. So now we go up to Data, and we can see over on the right there's a little solver button, and we click solver. Now the solver works by setting an objective cell. In this case, our objective cell, we have 2 objectives, but we only get to set one of them at the beginning. So we're going to set, our objective is to make f1 a value of 0 by changing cells are unknowns. So we're going to change both of our unknowns. So we drag across both of these, V7 to V8. And in this case, we have a constraint. Our constraint is we want the other f to also equal 0. So let's add a constraint that f2 is also equal to 0. Okay. So now we're saying make f1 equal to a value of 0 by changing cells x1 and x2 subject to the constraint that f2 is also 0. So that's how we set that up, and then we solve. And we can see that Excel was able to find a solution. This is close to 0, very close to 0, and here's our values for the unknowns. 0.6 and 4.23. So I wasn't too far off, to within one digit of accuracy, and that's a good way to use the solver. The second way we can use the solver, let's go back to another guess like 1 and 1. Okay. The second way we can use the solver is by combining the errors in F1 and F2, and then telling the solver to adjust the unknowns, x1 and x2, so that we minimize the sum of the square error. So if we minimize both the sum of the error in F1 and F2 at the same time, then we need to adjust both x1 and x2 to do that. So we can do that by adding these extra cells here, the error 1 squared. So the error will always be positive if we square it. So here we'll go equals F1, well, parenthesis, F1 minus what we want it to be, minus what we want it to be is 0, square it. So there's our error squared. It's 5, but it should be 0. So the error is 5 minus 0, which is 5. And then we square it to make sure it's positive. Okay. And then we do that for the other one, equals F2 minus what we want it to be, 0, and then square that. Good. And then we just find the sum of the square errors equals that one plus that one. There we go, 41. Now we're going to tell the solver, adjust x1 and x2 so that the sum is as small as it can be. So we go up again to the solver, and we click set objective, the sum, to the minimum. You can put 0 in there, but it sometimes doesn't work if you put 0. So it's better to just make the sum of the squares minimum by changing cells, x1 and x2. Here we don't need a constraint. So let's delete that constraint. Highlight it, delete it. Now we're all set up. And we can click solve. And okay. And we can see that the sum is practically 0, e to the minus 11. F1 and F2 are very small, and we have these same two values for the solution. Okay. So the advantage of method 2 is that you don't need to put the constraint functions in explicitly. You can do the sum of the square error and just make that sum minimum. And I use both of these. To find the other unknown, we found this one. We need to use guesses that are closer to the other side. So in this case, let's make x be minus 2, and x1 be minus 2, and x2 be 0, say. And then we'll go up to the solver and set the objective, and it's all set up, ready to go. Solve it again. And in this case, it went back to the same one as before. So this is an example where you don't always converge to the root that you think you're convergent to. So we can try maybe minus 3 and minus 3. And go to the solver and say solve. And we can do this over and over again. And that is an introduction to using the solver in Excel.